Good evening again. Exploring the Solar System, Part 2, Spacecraft. I thought I'd start, when I put this talk together, by thinking about how many spacecraft we have sent out into the Solar System. I started trying to count them up on the fingers of two hands and then realized I ran out of fingers. So in the end, I simply had to look it up, good old Google. And I found there were rather more than I had appreciated. Now, I know you can't read the names, but the number was absolutely huge. So I'm going to tell you about how we send spacecraft out into the solar system, how we actually get there. What are we going to do when we get there? Usually that's take images. How do we get those images back? And then again, I'll ask the question, where next? But just before we talk about that, let's just remind ourselves about the history. Ever since we've been sending spacecraft into space, the total number of spacecraft we sent into the solar system is absolutely huge. And I know you can't read the list, but there they are. I think it's up to date. The last one I've got there, I know you can't read it, but it's Europa Clipper, which was sent a few months ago. Perhaps I ought to double check that nothing else has gone up in the last couple of months that needs to be added to the list. I've got about 4 spaces there before I have to change this slide. But yes, the number of spacecraft we've sent into space to explore the solar system in some way or another. Some of the very early missions, the Apollo missions are in there as well, because we've sent them into space to study the moon and other things as well. But it's truly vast. If we want to go beyond the moon and think about going to Mars, which I mentioned in the last talk, then if we want to fly from Earth to Mars, let's just think about that in a very simplistic state, in a similar way to the orrery sitting on the side of the screen there. If we think about Earth orbit and Mars orbit, definitely not to scale, this is just a cartoon. If we want to get from Earth to Mars, we don't wait until Earth and Mars are as close as they could possibly be. We actually arrange it such that Earth, when we launch, and Mars, when we arrive, are on opposite sides of the solar system. That sounds very counterintuitive, to take the long way round, but actually it uses the least fuel. And what you actually follow is that blue line there. That's, if I take the orbits away, that is the orbit that gets you from Earth to Mars using the least fuel, called the Hohmann transfer. It takes about a year and a half, given the Earth goes around the Sun in about a year, Mars goes around the Sun in about 2 years. So it takes about a year and a half. And you might say, well, this is great, we can leave Earth and then we can arrive at Mars, and if for some reason we decide not to land on Mars, all we do is keep going and we'll come back to Earth again. That sounds very nice, except that it takes a year and a half to follow that blue curve, that blue ellipse. How long does it take Earth to go around the Sun? 1 year. So 1.5 years later, Earth isn't going to be there anymore. Earth is now going to be on the other side of the Sun. So unfortunately, you can't simply go to Mars and if you change your mind, go straight back to Earth again, because Earth won't be in the right place. This is one of the problems with getting to Mars. You've got to get the timing right. And that's why missions to Mars end up being more like 2 years rather than just the number of months to get there and the number of months to get back. But Mars is arguably the easiest planet to get to, simply being the next one out in the solar system. But back in the 1960s, it was realized that if we want to explore more of the solar system with spacecraft, if we want to get to the outer solar system, what we can do is a so-called gravity assist, sometimes called a slingshot maneuver, whereby we can launch from the Earth, and as we fly past Jupiter, let me just run that animation one more time so we can see it. If we fly from the Earth, as we pass Jupiter, we can use Jupiter's gravity to slingshot us, gravity assist. Notice it suddenly changes direction and picks up speed, and hence we can fly on and explore, for instance, Saturn, if we get the timing right. It was realized in the 1960s and 70s that the planets will be in about the right position such that we can use this slingshot. It means that we get there faster, because you can go faster by using the gravity assist from one planet to get to the next. You can go faster, and because you don't need to use fuel, you're just using the planet to give you an assist, you can actually save some weight on your spacecraft and use it for scientific equipment rather than fuel. So it's a double whammy. You get there faster and you can take more stuff with you in terms of cameras and equipment. This was done not only for Voyager 1, which had a gravity assist from Jupiter and then flew on to Saturn. That proved the idea, and Voyager 2 then launched from Earth, had a gravity assist from Jupiter, flew on to Saturn, got another gravity assist from Saturn and flew on to Uranus, got another gravity assist from Uranus and flew on to Neptune. It didn't need a gravity assist from Neptune because it was already going fast enough to leave the solar system, which was one of its aims, and it actually went over the pole of Neptune to get a better view of Triton, so it actually slowed down slightly when it went past Neptune. But still, the idea of using gravity assists is now an established way of getting around the solar system, simply because it uses less fuel. It's a little counterintuitive, but actually it's used by Bepi Colombo to get to Mercury. It's on its way to Mercury. It'll arrive in Mercury orbit fairly soon, but gravity assists have been used not to accelerate it, but to decelerate it. When you're going to the inner solar system, you want to slow down, and you can still use gravity assists to slow down, just like you can use gravity assists to accelerate and go faster. So gravity assists are used all over the place to save fuel. It's a very fuel-efficient way of getting around the solar system. When you visit these bodies, you want to take an image. Scientists want to take lots of measurements, but everybody on Earth says, show us the pictures. So you might want to measure the temperature or the pressure in the atmosphere, or you might want to measure the magnetic field. But basically everybody says, if you don't take a camera, it never actually happened. This is a very early image, as you can tell from the amount of noise in it. Any idea what it is?
Mars.
Reasonable guess. Actually, it's a little closer to home. The spacecraft was Luna 3. That gives you the clue. This is the far side of the moon. Remember, we've never seen the far side of the moon until a spacecraft has gone round and imaged it. So this was the far side of the moon, first imaged in the 1950s, before digital cameras. How on earth do you take a picture of the moon and get the image back to Earth when you haven't got a digital camera? So do you take a picture and then somehow fly the spacecraft back to Earth and hope it doesn't burn up as it comes back in? No, they had a different idea. That's just the same image with a little bit of modern noise reduction, just to show you there's not much there, but there are a few splodges, a bit like the near side, a few dark patches and a few light patches. But the question is that a reasonable image of the far side of the moon? And how did that image get back to Earth? No, they didn't take the film back to Earth. What they did is expose emulsion. You remember the old days when emulsion was exposed rather than digital technology? The film was developed on board. The exposure was taken, and then a little chemistry lab developed and fixed and dried the film whilst it was on board. And then it was scanned by a little flying spot, a cathode ray tube spot, scanned the negative in effect, and a photomultiplier picked up the light levels. And then the output of the photomultiplier was transmitted back to Earth as an electronic signal. Once it was received on Earth, then the image could be effectively constructed, a bit like a fax machine. You send an electronic signal, you then at the other end reconstruct the image. So that's an amazing way of taking images back in the 1950s before we had digital technology. You realise we've got it so easy now. We point, click, done deal. In the old days, nothing quite so easy. And just to show you how good that original image is, if you look at a recent 2009 image from Lunar Reconnaissance Orbiter, there's a high-resolution version of the far side of the moon. Notice that the original one, okay, lower resolution, but it's right. It's got all of the light and dark regions in the right place. So the original image, even though it was taken on film, developed on board and scanned, it still produced a genuine, reliable image of the far side of the moon. It wasn't until the 1960s that people said, this is ridiculous. We can't send film up there and develop it and send signals back. We need a better way of doing this. So the world's first digital camera was put onto a spacecraft. This is not the first spacecraft digital camera. This is the world's first digital camera. Digital cameras were built for spacecraft. The fact that you've got one in your phone is just a spin-off of the space development back in the 1960s. So underneath Mariner 4 is the digital camera. As Mariner 4 flew past Mars, as with many of these flybys, you've only got an hour or two as you fly past the planet, didn't go into orbit. That's a tricky maneuver. It flew past the planet, and all of the images were stored on tape. The tape's on a continuous loop. they hope the tape stops at the right point. Otherwise, it keeps recording, and if it flies past Mars and then looks into deep space, if the tape kept running, it would keep recording nothing, 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 and it would overwrite the data. So yes, the tape did stop at the right point after the flyby, and then at some point later, once the flyby had finished, then you rewind the tape and read the tape and send the images back to Earth. And this was Mars in 1965, basically the first digital image of another planet. Again, we can tidy it up slightly, remove some of the noise. And again, you can see the resolution isn't anything like what we're now used to with modern images from Jupiter and Saturn, etc. But for the 1960s, this was amazing that we could get digital image back from the flyby of another planet. We've now effectively visited every major body and a few of the minor ones as well. We've visited all of the planets and the occasional dwarf planet and a few asteroids and a few moons. And of course, there are lots of missions that in principle I could talk about, but again, in 25 minutes or so, I haven't got time. So I'm just going to pick a couple of missions to give you an idea of what is involved. So this is the Cassini mission. The Cassini mission to Saturn from 2004 until it was crashed into Saturn in 2017. Why was the probe crashed into Saturn rather than just powered down and left to drift and stay in orbit? Well, it's because that we have an inkling that the moons of Saturn, as well as the moons of Jupiter, are very interesting and are possible places where life might have evolved. The body of Saturn, the body of Jupiter, no, they are not conducive for life, but the moons may be. So at the end of its mission, it was deliberately crashed into Saturn to make sure it never accidentally crashed into any of the existing moons that could have possibly contaminated life there. This, in the bottom right, gives you an idea of the scale of the Cassini spacecraft. You can see it's quite large. Some people think these spacecraft are relatively small, like the rovers that we see on Mars, but actually these spacecraft can be quite huge. And on the left-hand side there, NASA have simply indicated some of the numbers. I'm not going to read through them all, but basically it's a reminder that billions of miles have been traveled by these spacecraft to get to the outer solar system. Millions of commands have been executed. In other words, the spacecraft is instructed, go to this place or fire your thrusters to try and go into this particular orbit. Orient yourself so the cameras are looking down at this part of the planet or this moon or these rings, etc. when we're dealing with Saturn. Huge amounts of data collected, hundreds and hundreds of gigabytes of images and other scientific data collected. And something like hundreds of different maneuvering engine burns to try and get them in the right place to take the right images. The reasons for Cassini going to Saturn is to study the planet, study the rings, study the moons. And if we think of what the Hubble Space Telescope can see of Saturn, a rather beautiful image of Saturn and its rings, if we look at the rings themselves and ask ourselves how much more detail can we see, not from a rather excellent space telescope here in Earth orbit, but what if we can get closer to the planet? Then we realize the Cassini spacecraft can see so much more detail in the rings themselves. So much detail, it starts to look like it's impossible to resolve individual ringlets. Each of these rings is basically trillions of individual particles all going around Saturn independently. Some of them are being shepherded by moons, so you get these various structures. It starts to look like a long playing record when you look at it in detail. We have to remind ourselves that the ring system, although being some 250,000 kilometers in diameter, its thickness is only measured in meters, perhaps a kilometer, but basically meters or tens of meters thick. It is the thinnest object, the thinnest structure in the solar system. At certain times in its orbit, the sun is in the same plane as the rings, and so the sunlight comes at an angle and starts to highlight bumps that you would otherwise find very difficult to measure. So there's the flat rings, but it's clear from the shadows cast by these bumps here that these bumps are sitting above or below the ring plane. So it looks like we've got sort of mountains. They're not mountains in the conventional sense because we've only got collections of tiny particles. But here, it was possible to get an idea of the dynamics of how these ring systems develop and how they evolve by looking at what structures we have at the edges of these ring systems. These bumps are perhaps a few kilometers or so in height, rather larger than most of the ring system, which is perhaps 100 times thinner than that. One thing you can't do from Earth is ever look at a planet like this from its shadow. Effectively, Cassini flew into Saturn's shadows, so we're looking at Saturn with the sun directly behind it. So the sun is illuminating the planet and the rings from behind. And whenever you get a backlit object like this, the way light scatters when it's coming directly at you rather than from over your shoulder tells you about the relative sizes of the various ring particles. So from Earth, of course, being relatively close to the sun, we can only ever see Saturn with the sun shining over our shoulder. But Cassini was able to look at it from the opposite direction to get more information about how the ring system is put together. A stowaway, well, not really a stowaway, but a small interloper here was Huygens, a spacecraft on the side of Cassini. The idea is the Cassini spacecraft would look at Saturn and the rings and to some extent the moons, but they wanted to investigate Titan in even more detail because Titan has such a thick atmosphere, it's very odd. So basically they flew Huygens on a parachute into the Titan atmosphere. The atmosphere is so thick and hazy we can't see the surface from Earth or from orbit. So it needed a spacecraft to go into the atmosphere before we could actually see what Titan is actually made of. As Huygens' lander plunged through the Titan atmosphere, it took images as it came down. And although we didn't know what Titan was made of in terms of its structure, we now know it has mountains, and it has lakes, and it has rivers, and it has clouds, and it has rain. Not water, because it's too cold out there in the far reaches of the solar system, but it looks like the geological features which are the analogue of the sort of features that we recognize here on Earth and on other planets. So unlike Mars, where there used to be running water, it looks like there is still running liquid on the surface, and rivers and lakes and clouds and rain, etc. An entire ecosystem that is worth studying. And remember what I said last time about Ingenuity on Mars, the helicopter. We would like to send a helicopter to Titan to study in even more detail what's going on. Huygens simply flew in and then crashed into the surface. We would like to send a helicopter to explore even more about this landscape. We've also sent missions to Jupiter. The most recent was Juno in 2016. Again, a whole load of numbers here, billions of miles traveled, terabytes of data collected, millions of commands executed in terms of flying close to Jupiter and its moons of interest as well. There's a rather harsh radiation environment around Jupiter, so the way Juno is working is it's in a very elliptical orbit. It spends most of its time away from Jupiter where it's safe, and every once in a while it does a dive over the cloud tops to get a much closer view of the planet. So we can get an idea of what Jupiter is like. That's the sort of familiar view that we might get from Earth. If we just unwrap it to remind ourselves, what we're actually looking at is a whole load of winds, some of which are going east to west, some of which are going west to east, and we get storm systems like the red spot there, the great red spot. What are the different colours? Well, it is assumed that what we're looking at are different elements, perhaps different elements being churned up from different depths that give rise to the colours. Maybe we're looking at sulfur and phosphorus in some cases, or ammonia ice in other cases, giving us this colour contrast. What Juno is able to do is take a really close look at Jupiter by swinging in over the pole and then going past the equator all the time, looking at the cloud tops. Notice these flashes of light here. There's lightning. So lightning in the storm systems of Jupiter. It's sweeping down. This is time-lapse taken over an hour or two, and it's sweeping only a matter of thousands of kilometers above the cloud tops. And it swings past, and then as it comes out back into its large elliptical orbit, it looks back at Jupiter and again sees huge amounts of detail in the storm systems, and as well as the rather salmony coloured equator, we have these slightly bluish poles as well. We can enhance the colour a little bit to make those colours pop. It's not quite natural colour, but it shows us there's an awful lot going on in there. Given that the structure is dependent on the storm systems, the colours are dependent on which elements are being dredged up, perhaps at different altitudes. It's difficult to tell when you're at this distance if you're looking at all the same altitude or whether you're looking at different depths. There were some images like this one. Yes, I know it looks like a watercolour left out in the rain, but basically this dark object here, they're now debating, are we actually looking at a vortex? Are we looking at something which is a deep dive into the atmosphere of Jupiter? Are we looking into a keyhole down to lower depths there? The dark spot, perhaps a vortex of clouds. This was imaged when the Juno spacecraft was only some 15,000 kilometers or so above the cloud tops. And it's taken hundreds, if not thousands of images like this, which are helping us understand the Jovian system. This is a little animation of some of that, again, with artificially enhanced colors. It reminds you just how complex these cloud systems are in terms of how they're interacting with each other. If you think it's difficult to predict Earth weather, imagine having a storm system like this, trying to understand such a chaotic system as to why it's doing what it's doing. And we should remind ourselves that although we've had fantastic images from Cassini of Saturn and Juno for Jupiter, and other planets have been explored with the Voyager probes and more recent probes as well, we should remind ourselves that the Sun is accompanied by 8 planets, but that's not the entire solar system. The solar system is so much more than just the Sun and 8 planets, even if we take into account the occasional asteroid and objects in the Kuiper Belt, for instance, as indicated by the orrery on the side there. New Horizons spacecraft visited Pluto and then kept on going, a bit like Voyager's, heading out of the solar system due to a gravity assist. And we're trying to figure out, are there objects in the Kuiper Belt beyond Pluto that New Horizons could go and visit? It's a bit difficult because it hasn't got much fuel, but perhaps we can figure out what might be on its path that are worth photographing in years to come. So New Horizons, although it's done its job of looking at Pluto, might still have a few tasks to perform when it's looking at other objects in the Kuiper Belt. And the solar system contains over 300 moons and counting, because we keep finding them, especially moons of Jupiter and Saturn. There's just a very small selection of some of them. There's our familiar moon in the bottom right there. That looks more like the Death Star from Star Wars rather than a moon. But yes, all of these objects, the larger ones tend to be almost spherical. The smaller ones tend to be a little more potato-shaped. But there's all sorts of moons out there, and if we look at the largest moons rather than a selection of them, these are the largest ones, the major moons of the solar system. There in the middle is Titan, shrouded by haze. Remember, we can't see the surface, which is why we sent the Huygens lander down there. And the top 4 are the Galilean moons of Jupiter: Io, Europa, Ganymede, and Callisto. And if we think about those, Io is a volcanic world being very close to Jupiter. It's being stressed. It hasn't necessarily got the same plate tectonics as the Earth, but it's being stressed in a way which is effectively keeping it heated and producing a lot of volcanic systems. But a lot of interest recently has been not necessarily in Io, but the other 3 moons, the so-called ice moons. All of them appear to be covered in ice, but there is evidence, tantalizing evidence, which needs to be verified, that they all seem to have subsurface oceans. So these are, although they look like lumps of ice, these are more perhaps accurately called water worlds that just happen to have an ice coating on them. There's more water on these moons than there is in all of the Atlantic and the Pacific put together. So there's a huge reservoir of water. As far as we know, it can be water, not necessarily fresh water. It might have other elements dissolved in it. Remember, the requirements for life are you need the right compounds, you need ideally water or some such solution to allow those compounds to get together and molecules to actually form more complex molecules, and you need an energy source. It looks like all of those 3 ingredients exist on these ice moons. So these are prime candidates for life in the solar system, more so than Mars. Mars is easier to get to, but these, many people believe, are more likely to harbour life than Mars does. And that's why there have been two recent missions. JUICE over a year ago and Europa Clipper in the last few months have been sent to Jupiter. JUICE is Jupiter's icy moons. Great name. That's an ESA mission, and Europa Clipper is going to Europa, and it will be looking at the other moons as well. There's Europa, the second one, but it might be taking a gander at the other moons as it goes. But the main emphasis will be on getting as much data from Europa as possible. So ESA and NASA independently are both interested in these icy moons, and they sent two missions in parallel, as it were. When you're going to these outer parts of the solar system, it's not so far that solar panels can't work. So this is about the limit for where you want to go with solar panels. So solar panels will be fine. But of course, we're talking about vast distances when we're sending probes to Jupiter. How do we get the data back? We would like to get the scientific data back. We would like to get images back. How has that been done for all spacecraft up until now? Well, basically, it involves a large radio dish, as we saw with Cassini, for instance. A large radio dish will then be pointed back to Earth, and the radio signal will be sent to Earth, and then an even bigger radio dish on Earth will pick it up. And hopefully, even if it's a very weak signal, pick up the radio transmissions and then decode as this is an image, this is a video, this is scientific data, etc. We've been doing that for many, many decades, sending data via radio signals. But relatively recently, people have said, why use radio? Wouldn't lasers be a much better way of sending data? Lasers would need less power and, in principle, much higher bandwidth. In other words, you can get much more data into a laser beam than you can get into a radio beam because of the frequencies involved. Frequencies are much higher. So instead of having a radio dish on Earth picking up the radio signals, you would have an optical telescope, such as, for instance, here, the 5-meter Hale telescope, which was used as a test to see, is this viable? A spacecraft was sent to the asteroid called Psyche. It was sending back data by radio, but as a test, they thought, let's try this. Let's send a laser on the same spacecraft, and as well as sending radio data back, let's try sending a laser beam back from the spacecraft and see if we can pick it up in an optical telescope like the Hale telescope. What are we going to send? Well, we could send an image. That's not a real test. We're trying to work out whether the data rates can be much higher than they can with radio. So rather than just send a high-resolution image, they figured they would send a high-resolution, high-definition video and then see how quickly they could get the data from the spacecraft, hundreds of millions of kilometers away, back to Earth. And the video they chose for a laser beam test was a cat chasing a laser beam. So they took this high-definition video, I've reduced the resolution just for the purposes of this PowerPoint, and they sent this video back. And at a distance of 50 million kilometers, they got a data rate of 260 megabits per second. That's faster than some people can get on their broadband when they're picking up a signal from 10 miles away. And this is 50 million kilometers. Even when the spacecraft was at a distance of 400 million kilometers, the other side of the solar system, they could still get a data rate of more than 8 megabits per second. Fast enough for Netflix streaming times 8, probably. So they've proved that laser beams can indeed send data back much faster. So maybe in future missions, not just yet, but future missions, they will be using laser transmission rather than radio transmission, and maybe we can get high-resolution images and high-resolution video back much faster than we could at present. So if you want to know more, the Cassini mission is now dead because it's now been flown into Saturn. Bepi Colombo is on its way to Mercury and will get there soon. I've said New Horizons is on its way out of the solar system. I've told you a little bit about Juno, which is now coming to the end of its life studying Jupiter. And we've got two new missions, the JUICE mission on its way to Jupiter's icy moons and Europa Clipper on its way to Europa. So if you want to know more about past missions, or in particular those missions, those web pages, and I've got handouts here if you don't bother writing down the web pages, I'll make these available to you via Bob at a later date. So there's lots of information out there if you want to learn more about how we explore the solar system with spacecraft. Thank you very much.